Hello everyone. In this session of programming and network properties of advanced computer architecture, we will learn about the things like hardware and software parallelism, data dependency, grain size, granularity, and latency. In the last session, we have already seen what are the types of data dependency, what is hardware and software parallelism. Just briefing out the things what we have learned in the session 1. We have seen data and resource dependency. The data and resource dependency is the ordering relationship between statement is indicated by data dependency, and we have seen that there are 5 types of data dependency: flow dependency, entity dependency, output dependency, input output dependency, and unknown dependency. So these are the 5 types we have already seen in the last session. Just go through the last session for the detailed understanding. We have seen hardware and software parallelism. Like hardware parallelism, this refers to the type of parallelism defined by machine architecture and hardware multiplicity. Hardware parallelism is often a function of cost and performance trade-off. It displays the resource utilization pattern of simultaneously executable operations. It can also indicate the peak performance of the processor resources. On the way to characterize the parallelism in a processor is by the number of instruction issues per machine cycle. So if a processor issues k instructions per machine cycle, then it is called a k issue processor. So a conventional pipeline processor takes one machine cycle to issue a single instruction, and these types of processor are called as one issue machine with a single instructions pipeline in the processor. For example, we have Intel i960CA, which was having a 3 issue processor with one arithmetic, one memory access, one branch instruction issues per cycle. So this is how what the hardware parallelism is. So now the software parallelism, that it is defined by the control and data dependency of a program and is revealed in program's flow graph. That is, it is defined by dependencies within the code and is a function of algorithm, programming style, and compiler operations. So this type of parallelism is revealed in a program profile or in the program flow graph, and software parallelism is the function of, as I said, algorithm, programming style, and program design. So the program flow graph displays the patterns of simultaneously executable operations. Now next we will see about grain size and latency. So mostly this section introduces the basic definition of computational granularity or level of parallelism in a program, and communication latency and scheduling issues are illustrated with programming examples. So now let us see what is grain size and latency. Mostly grain size or granularity is a measure of the amount of computation involved in a software process. So the simplest measure is to count the number of instructions in a grain, that is in the program segment, and the grain size determines the basic program segment chosen for parallel processing. Grain size are commonly described as fine, medium, or coarse depending on the processing level involved. So latency, basically we have seen what is the grain size. Now latency is a time measure of the communication overhead incurred between machine subsystem. For example, the memory latency is the time required by a processor to access the memory, and the time required for two processors to synchronize with each other is called as synchronization latency. Remember, memory latency and synchronization latency are different. Memory latency is the time required by the processor to access the memory, and the time required for two processors to synchronize with each other is called as synchronization latency. Mostly parallelism has been exploited at various processing levels. So in this picture you can see that there are 5 levels of program execution represent different computational grain size and changing communication and control requirement. So the lower the level, the finer the granularity of the software processes. So here you can see that there are total 5 levels. Level 1 is instructions or statement. Level 2, non-recursive loop or unfold iteration. Level 3, procedure, subroutine, task or coroutines. Level 4, subprogram, job steps or related parts of a program. And level 5, jobs or program. So basically these are the 5 levels. So as I said, parallelism can be exploited at various processing levels, and we have this 5 level of a program execution representing different computational grain size and changing communication and control requirement. So the lower the level, finer the granularity of software process. So in general, the execution of a program may involve a combination of these levels. The actual combination depends on the application, formulation, algorithm, language, program, compilation support, and hardware characteristics. So we characterize below the parallelism level and review their implementation issue from the viewpoint of programmer and of a compiler writer. So in this diagram, see that at the lowest level, a typical grain contains less than 20 instructions called as fine grain. Depending on individual programs, fine grain parallelism at this level may range from 2 to 1000. So, uh, like if there are some of the grains, fine grains, which has more than 20 instructions, then it won't become in a lowest level. At the lowest level, a typical grain contains less than 20 instructions, and hence we called it as a fine grain. So level 1 and level 2 comes under fine grain because they have less than 20 instructions, and hence we are calling it as a fine grain. So remember, level 1 and level 2 comes under fine grain, like instructions or a statement, that is level 1, and level 2 non-recursion loops or unfolded iteration, this comes under fine grain. So the exploitation of fine-grained parallelism can be assisted by an optimization compiler, which should be able to automatically detect parallelism and translate the source code to a parallel form, which can be recognized by the runtime system. So instructions level can be detected and exploited within the processor. So the medium grain size having more than 20 instructions, like level 3 is procedure, subroutine, task or coroutines. Level 4 subprogram, job, steps or related parts of the program. So this comes under a medium grain which has more than 20 instructions. And last we have a coarse grain, that is job or program. In detail we will see what exactly a subprogram instruction is, what is job or program, and what is subroutine program, and what are these instructions. So next let us see the first concept, what is instructions level parallelism. So in the instruction level parallelism, they are a fine grain or a smallest granularity level typically involves less than 20 instruction, as we have seen, that is it is called as fine grain. So fine grain when we will call if it has less than 20 instructions. So the number of candidates for parallel execution varies from 2 to 1000, with about 5 instruction or statement being the average level of parallelism. Next we have a loop level parallelism. Now, in the loop level parallelism, this corresponds to a iterative loop operation. A typical loop contains less than 500 instructions. Some loop operation, if independent in successive iteration, can be vectorized for pipeline execution or for lock step execution on SIMD machine. So some loop operations can be self-scheduled for parallel execution on MIMD machines. A loop level parallelism is often the most optimized program construct to execute or a parallel or a vector computer. So however, recursive loop are rather difficult to parallelize, and vector processing is mostly exploited at the loop level. So it is most optimized program construct to execute on a parallel or a vector machine. And remember, in the loop level, typically loop has less than 500 instructions. As we have seen in a fine grain, they are less than 20 instructions, and in the loop level, they have less than 500 instructions. Next, we will see about procedure level parallelism. These level correspond to medium grain parallelism at the task, procedural, subroutine, and coroutine levels. Remember, these correspond to a medium grain parallelism. So a typical grain at this level contains less than 2000 instructions. Detection of parallelism at this level is much more difficult than at the finer grain level, and interprocedural dependency analysis is much more involved and history sensitive. So communication requirement is often less compared to the required MIMD execution mode, and SPMD execution mode is special case at this level. Multitasking also belongs to this category, and significant efforts by a program may be needed to restructure a program at this level, and some compiler assistance is also needed. So here interprocedural dependency analysis is difficult. Detection of parallelism is more difficult than what we have seen in a small grains. Communication requirement is less than the instruction level, and multitasking belongs to the this level of parallelism, that is procedural level. Multitasking is very easy. Next we will see subprogram level parallelism. Now this corresponds to the level of job step and related subprogram. The grain size may typically contain 10 or hundreds of instructions, hundred thousands of instructions, and job step can overlap across different job. Subprogram can be scheduled for different processors in SPMD or MPMD mode, often on message passing multi-computers. Like multiprogramming on a uniprocessors or a multiprocessor is conducted at this level, and traditionally parallelism at this level has been exploited by algorithm designer or programmers rather than by compilers. So good compiler for exploiting medium or a coarse grain parallelism requires suitability different parallel programming language. Here in subprogram level, multiprogramming conduct at this level. Next we have job or program level parallelism. Now this corresponds to the parallel execution of essential independent jobs on a parallel computer. So mostly corresponding to execution of essential independent jobs or program on parallel computer. So the grain size can be high as millions of instructions in a small program. So for supercomputers with a small number of very powerful processor, such coarse grain parallelism is practical. So if there are any of the supercomputers which have a small number of very powerful processors, then this comes under coarse grain parallelism. So the job level parallelism is handled by the program loader and by the operating system is general. So in this job level parallelism, time sharing or space sharing multiprocessor explore this level of parallelism. So in fact, both time space sharing are extension of multiprogramming. So in this case, both the time sharing and space sharing are extensions of multiprogramming. So to summarize, fine grained parallelism is often exploited as instructions or a loop level, preferably assisted by a parallelism or vectorizing compiler. So medium grain parallelism at the task or job step demands significant role for the programmer as well as a compiler, and in a coarse grain parallelism at the program level relies heavily on the effective of OS and efficiency of the algorithm use. So shared variable communication is often used to support fine grained and medium grained computation. Like as I said, we have three types of grains: fine grain, medium grain and a coarse grain. Now fine grain, already we have seen what comes under fine grain. So there are less than 20 instructions. If there are less than 20 instructions, it comes under a fine grain, and if there are less than 500 instructions, it comes under a medium grain, having loop level parallelism and procedural level parallelism which has less than 2000 instructions. So to summarize, fine grain, medium grain and coarse grain. Fine grain parallelism is often exploited at instructions or a loop level. Remember, this is very important. Fine grain parallelism is often exploited at instruction or a loop level, preferably assisted by a parallelism or a vectorizing compiler. So in next is we have medium grain parallelism. So medium grain parallelism at the task or job step demands significant role for a programmer as well as a compiler, and in a coarse grain parallelism at the program level relies heavily on the effectively OS and the efficiency of the algorithm used. So shared variable communication is often used to support fine grained and medium grained computation, whereas message passing multi-computers have been used for medium or a coarse grain computation. Like message passing multi-computers are very much demanding, which contains medium and a coarse grain computation. So massive parallelism is often explored at the fine grain level, such as data parallelism or SIMD or a MIMD computers. So remember, there are total 5 levels and instruction levels. And from that 5 instruction level, we have loop level parallelism, procedure level parallelism, instruction level parallelism, subprogram level parallelism, job or program level parallelism. We have seen what exactly the loop level parallelism is, procedure level, subprogram level, and job level parallelism. Now next we will see about grain packaging and scheduling. So before moving to the grain packaging and scheduling, let me tell you what is communication latency. So by balancing granularity and latency, one can achieve better performance for a computer system. Various latency are attributed to machine architecture, implementing technology and communication patterns involved. So the architecture and technology affect the design choices of for latency tolerant between subsystems. In fact, latency imposes a limiting factor on the scalability of the machine size. For example, over the year, memory latency has increased with respect to processor cycle time. So, various latency hiding techniques can be used. We have already seen what are the latency hiding technique in the previous chapter. So, the communication patterns are determined by the algorithm used as well as by the architecture support provided. So next we will be moving ahead with a grain size, grain packaging, packing and scheduling. So the as I said, the communication issue thus involves the reduction of latency and complexity, the prevention of deadlock, minimizing blocking in the communication pattern, and the trade-off between parallelism, communication overhead. So these techniques can be minimized to prevent deadlock. We use the grain packing and scheduling. So there are two fundamental questions to ask in parallel programming, that is, how can we partition a program into a parallel branches or a pieces like program module, micro task, or a grain to yield the shortest possible execution time. So that how can I partition a program into a parallel pieces to yield the shortest execution time. And another question is, what is the optimal size of concurrent grains in a computation. So there are these two questions asked for a parallelism before moving with the grain packing and scheduling. So this grain size problem demands determination of both the number and the size of grains or micro task in a parallel program. So of course the solution is both problem dependent and machine dependent. So the goal is to produce a short schedule for a fast execution of subdivided program modules. So there exists a trade-off between parallelism and scheduling synchronization overview. The time complexity involves both computation and communication overhead. So the program partition involves the algorithm designer, programmer, compiler, and operating system support. So this is how the grain packing and granularity is. As we all know, the grain size is a measure of number of basic machine cycles needed to execute all the program operations within the node. And the basic concepts of program partitions, like for example program graph, is too different from a grain size. So a program graph shows the structure of a program basically. So we need to have a graph which shows the program structure having n pairs, having edge level vertices and vertices with the edges. So this is how the grain size or the fine grain corresponding to a graph could have been shown. So till now we have seen what is hardware parallelism, software parallelism, what are data dependency, what are the types of data dependency. We have already seen the 5 types of data dependency. Then we have seen in this PPT that what is grain size, what is latency, and we have seen this diagram consisting of 5 levels of program instructions like increasing communication, demanding and scheduling overhead, having the 5 levels, level 1 to level 5, with which is categorized into fine grain, medium grain and coarse grain. We have seen that which instructions comes under fine grain, which instructions comes under medium grain, and which instructions come under coarse grain. So higher the degree, we have seen that there is a lesser the parallelism. So we seen the types of instruction level parallelism, loop level parallelism, procedure level parallelism, subprogram level, job and program level parallelism. We seen these 5 types of parallelism. Then we have seen that grain packaging and scheduling. So one approach to the problem of parallelism or scheduling, that comes under the trade-off between the time spent scheduling and the synchronization parallel grain and the speed up obtained by parallel execution, which we called it as a grain packing. So these concepts are covered in this PPT. I hope you have understand the concept. If you have any doubts, feel free to message me. Thank you.